Hello everyone. This is Gayatri Priya, Assistant Professor in the Department of ECE of RMD Engineering College. In today's sessions, we are going to discuss a topic on VLSI design, that is Schmitt Trigger. Right. In our earlier classes, we have done the fundamental concepts of Schmitt Trigger. Yes, the Schmitt Trigger is a comparator circuit. So it is just going to make use of a positive feedback. So positive feedback in the sense the portion of the output is fed back to the already existing input signal, but it is going to remain in phase. That is, the phase shift is going to be 0 degree and or 360 degree. Right. Here we are just going to make use of a comparator or a differential amplifier. So actually we are going to compare. If we are going to apply the input as a sinusoidal waveform and we are going to give a threshold voltage. Whenever the sinusoidal input crosses the threshold, we will be having the transition. Hence, the other name for Schmitt trigger is called trigger. That is, the output will be retained until the input is changed. How the input will be changed? Whenever it crosses the threshold, we will be changing the output. That is, the output will be moved from 0 level to the 1 level or from the low level to the high level. Hence, this Schmitt trigger is otherwise called as regenerative comparator. So, regenerative means positive feedback, since the phase shift is going to be 0 degree or 360 degree. In other words, if I could say in the sense, the output and the already existing input are going to remain in phase with each other. So this is a comparator. That is, the output is nothing but it is going to be the comparison of the input and the threshold. Whenever the input crosses the threshold, whenever it exceeds the threshold, we will be having a state transition in the output voltage. Right? So that is, it is going to have a major two important properties. The first one is, even though the input is going to change in a very low level, we are going to get a drastic variation in the output. We already told, if the output is already at 0 level, when the threshold point meets, it automatically goes to the high level, that is 1. The next important property is that whenever we are having a switching threshold, that is from low to high or from high to low, okay, we would get a hysteresis loop. That is, the difference between these two threshold voltage, Vm plus and Vm minus, is called the hysteresis voltage. So let us see how this hysteresis loop is obtained. Okay, the left hand side we could see the voltage transfer characteristics. In x-axis we have taken the input voltage and in the y-axis the output voltage is taken. That is, this curve explains the variation of the output voltage with respect to the input voltage. Right? So here Vm minus and Vm plus are the threshold points. Or we can say this is the low threshold point and upper threshold point, LTP and UTP. So LTP in the sense whenever the signal is going to move from low to high. And this is from high to low. So this V0H and V0L are nothing but low output voltage and low high voltage. Right? So this forms a hysteresis loop. Okay? And the right hand side shows the schematic symbol of the Schmitt trigger. Right? So that is, it is going to produce a square waveform. Even though the input is going to be a non-square waveform. For example, if the input is going to be sinusoidal waveform, we will be obtaining a square waveform because we are going to have only two levels. One is low level, the other one is high level. That is 0 and 1. Our output is going to be fluctuating between zeros and ones. Right? And the main use of the Schmitt trigger is to suppress the noise. That is, whenever the input is going to be a noisy signal or a slow varying input signal, we have told in one of the properties of the Schmitt trigger that for a small change in the input, we are going to get a fast range of output. So in that sense, it is going to produce a clean, digitalized output signal. It is used to reduce the noise. It is used to suppress the noise. suppress the ringing on the signal. Ringing on the signal in the sense the same type of signal is going to be repeated at varying frequency. Yeah, that is being depicted in this diagram. The left hand side is going to be an oscillating sinusoidal waveform. This is an example for a decaying type of oscillation. Okay, Vm minus and Vm plus are going to be the LTP and UTP of the Schmitt trigger. So when this type of signal is going to be passed to a Schmitt trigger, it is going to produce a proper pulse signal, right? That is T0 plus Tp. Here Tp is going to be the pulse time. Yes, the main advantage and main application of the Schmitt trigger is noise suppression. Yeah, here comes the CMoS implementation of our Schmitt trigger. Right, we know M1 and M2. So this is somewhat acting as an inverter. And M3 and M4, this is also acting as an inverter. Okay, these output are being connected to a buffer. You could see when the input is going to be at 0, obviously this is passed through this inverter. Here the output will be 1. So if this 1 is passed here, we will be getting the output as 0. So both input and output voltage remains 0. Right. So if V out is 0, what happens? That 0 is being coupled to this PMOS transistor, that is M4. Right. Which makes this PMOS transistor to be turned on. If in a CMOS inverter, if PMOS, that is the pull-up network, is turned on, obviously the pull-down network is going to be turned off. So in this moment, M1, M2 and M4 are responsible to produce the output. That is, it moves the output from 0 level to the 1 level. If V out becomes 1, what happens? It will turn off your M4 and turn on M3. M3 is nothing but a NMOS transistor, that is a pull-down network. Okay. Now this M1, M2 and M3 combinedly operate. Okay. So that the output of the Schmitt trigger will be moving from high level to the low level. If V out comes 0, again M4 will be turned on and M3 will be turned off. And this process is cumulative, so that it just produces a square wave. Hope you understand the today's session on Schmitt trigger. Thank you.